In this class, we're going to get into some real counting. Let's start with an example to see how a principle can be worked out and then generalized. Ksenia, that would be me, is picking an outfit to wear to school, an everyday morning problem. Today, she is choosing between 2 different blouses and 3 different skirts. How many different outfits can Ksenia put together? So, because the numbers are so small, we can actually write out all the possible options. I have 2 different blouses. Let's call them B1 and B2, and 3 different skirts. So let's call them S1, S2, and S3. In how many different ways can I put together a blouse and a skirt? So I can say, well, blouse 1, skirt 1, or blouse 1, skirt 2, blouse 1, skirt 3. And of course, I can repeat all of the same things, but with blouse 2 as my option. Once I've listed all of these, I think these are all the possibilities. I can wear either blouse 1 or blouse 2 and run through all the skirt possibilities for each one of those. So altogether, I have 6 options. The other way to represent this pictorially isn't with this table-like form, but what we call is a tree diagram. I can start off from the beginning by placing a vertex or a node here, and then draw out branches for all the possible options. So for example, if I'm picking a blouse first, I have my options as blouse 1 and blouse 2. And then going from, for example, this vertex, once I have picked my blouse, I can pick skirts. And here I have 3 options for each of the 3 skirts. Skirt 1, skirt 2, skirt 3. Same for the second blouse. I have skirt 1, skirt 2, skirt 3. Now, at every endpoint here, that means that I have followed the 3 branches from the beginning. So for example, for this node, that means I've picked out skirt 1 and blouse 1. For this node, vertex, that means I've picked out skirt 3 and blouse 1, going from the beginning. So the endpoints here represent all the possible options, which of course are the same as here. Notice that I can draw my tree diagram in the opposite order. What if I wanted to pick a skirt first? Then I will start off without either the skirt or the blouse. I will first have 3 branches for 3 possible skirt options. And then for each skirt, I will have 2 possibilities for a blouse. Blouse 1, blouse 2, 1, 2, 1, 2. And then the end result is listing the exact same possibilities, but in a slightly different order, right? So again, each one of these end vertices represents a complete outfit, but they're listed differently. The tree diagrams help us see a little bit better where this number 6 comes from. For example, for the first tree diagram, I picked 2 options here, and then for each of the 2, I had 3 possibilities. So this 6 actually comes from the fact that I have 2 options for blouses and 3 options for skirts. Multiplying the 2 together gives me all the possible options for the outfit. Let's consider a slightly different scenario. Next day, I'm again picking out what to wear. This time, I want to pick one of 2 dresses or one of 3 pantsuits. So notice the difference. In the first question here, in the first example, the connector was an and in this one, the connector is an or. In the first question here, I had to pick blouse and a skirt. Here, I get to pick either a dress or a pantsuit. What are my possible outfits? So let's say my dresses are D1 and D2, and my pantsuits are P1, P2, and P3. So what are my possibilities? Well, I can either choose dress 1 or dress 2. If I choose a dress, I don't get to wear a pantsuit. So those are my only options. What about if I choose pantsuit? So I can choose the first one, the second one, or the third one. And these are all of my possibilities. So altogether here, I have 5 options for outfits, which is composed by adding 2 options for either the dress or 3 options for the pantsuit. So 2 different scenarios, seemingly similar numbers, but the way that they're put together results in very different outcomes. And here is where we get our two general principles, the multiplication principle and the addition principle. The multiplication principle is applied to a task that is composed of consecutive choices. The additional principle is applied to a task where we have one action or another action, but they cannot be performed at the same time. So let's go through the general statements. If choice 1 can be performed in M1 ways and choice 2 can be performed in M2 ways, then the complete task that is consisting of consecutive choices can be performed in M1 times M2 ways. So just like in my example with the outfit, the very first example here, I had to pick a blouse and then follow it up by also picking a skirt. 2 choices here followed by 3 choices there means that I have to multiply the number of possibilities together. This can be generalized to any number of tasks. So the generalized version will be if I have M1 choices for one task and M2 choices for another and M3 for the third and so on, as many of them as I have, then the total number of ways in which I can perform the complete task is going to be multiplication of all of those ways. The addition principle consists of the exact same setup, except for I have 2 actions that I can perform one or the other one of, but not together at the same time. In this case, we will have to add the 2 options together. And again, that is already been illustrated with an example above, where I get to pick either dresses or suits, but they cannot be done at the same time. And not very surprisingly, the generalized form here will be situated much the same way. If I have M1 choices for one action and M2 choices for another, M3 for the next, and so on, if I have to choose the complete way to do this, but these tasks cannot be performed at the same time, then I'm going to be adding all of them up. So let's review. The multiplication principle is applied when the tasks are consecutive and they're joined by an action that is indicated with the words like and. The addition principle is applied when you have a combination of 2 tasks or more that cannot be performed at the same time, and the word that connects them would usually be an or. Let's see how we can apply these 2 principles in a setup that is quite familiar in this counting world and will actually be probably familiar to those of you who have taken computer science courses. In thinking of the number of ways words or strings can be put together. So a word in mathematics or computer science is just a string of letters. In English or any other language, a word is a string of letters that means something. In mathematics, we think of it as just a string of letters. So for example, a word dog is only a word in English, but the same letters can be permuted together, for example, DGO, and in mathematics, that would still be considered a word, whereas it actually means nothing in English. First question, how many 3-letter words are there? We're going to have to think of how we actually put words together. So it's a string of letters. They're 3-letter words, which means that I'm thinking of putting one letter after the other, one at a time, consecutively. How many choices do I have for the first letter? If we're talking English, there are 26 letters in the alphabet. So for the first choice, I have 26 letters to choose from. For the second choice here, for the second letter, how many choices do I have available? Well, I'm still picking out the entire alphabet, so I still have 26 choices here. And the same for the third letter. I have 26 choices here as well. The tasks are consecutive. I have to pick letter 1 and letter 2 and letter 3, which means that altogether I'm going to multiply them, resulting in 26 cubed in this case, for the total number of 3-letter words. You can plug this into your calculator and see how big the number actually is. How many 3-letter words are there that have no repeated letters? So in terms of the original setup, we have the exact same situation. I'm going to have 3 spots for 3 letters. Now, for the first letter, how many choices do I have? I have 26 choices. For the second letter, how many choices do I have? I cannot repeat letters, so whatever letter was chosen for the first position cannot be chosen for the second one. Let's say if the letter here was K, I have all the possibilities here except for K. So the letter that has been used up now has to be taken out of the circulation. So if I had 26 choices for the first letter, for the second letter, I have 25 choices because I cannot choose the letter that was chosen for the first position. What about the third position? There's no repeated letters, so I cannot repeat the letter that was in the first spot, and I cannot repeat the letter that was in the second spot. I start with 26 letters. There are 2 letters that I've already chosen that I cannot take. Therefore, the total number of options for the third letter is 24. Because again, these are consecutive tasks, I have to choose the first letter and choose the second and choose the third. I will be multiplying these numbers together to produce the final answer. 26 times 25 times 24. If you compute this number separately on your calculator, you will see that it's less than this number. There are fewer letters with the restriction of no repeated letters than there are letters that have no restrictions on anything altogether. How many 3-letter words are there if the last letter must be a vowel? So a vowel in English is one of the following 5 letters: A, E, I, O, and U. There are 5 possible vowels. So I'm still after 3-letter words. The last letter must be a vowel. So the last letter, I don't have 26 choices anymore. I only have these 5 choices to pick from. What about the first 2 letters? I have no restrictions on those. They can be anything, they can be repeated. I don't have any specific information telling me about that. So for the first letter, I have 26 choices. And for the second letter, I again have 26 choices. Now notice that once again, I'm in the multiplication principle. I have to pick the first letter, that can be anything, and the second letter, that can be anything, and the last letter, that has to be one of these 5 vowels. So altogether, I'm going to have 26 times 26, so 26 squared times 5. How many 3-letter words have no repeated letters and in a vowel? So now I have a very specific condition that narrows this down even further. They have to have vowel in their last position, but also I can't repeat any of the letters. So normally, a good rule of thumb is to start with the most restricting condition and work from there. The most restricting one is it must end in a vowel. The last letter must be one of these 5. So for the last letter, I have 5 choices. What happens next? Well, then I have to actually pick what goes here. I'm not allowed to have repeated letters. So whereas in the previous example, I had 26 choices, here, the vowel has already been chosen and I cannot pick whichever one goes there, which means that for the first letter, I only have 25 choices, given the fact that I have picked a vowel to go in the last spot already. This one is even more restricted still. I originally had 26 possibilities for this letter, but now I've picked the other 2 and I'm not allowed to repeat anything, which means that here I'm going to have 24 choices in total. Right? So sort of moving one letter at a time, but maybe not in the left to right direction. Once again, multiplication principle is at work. I have to pick the first letter and the second letter and the last one as the vowel. So I'm going to multiply all of these together. Okay, and for the last part of this question, how many 3-letter words have no repeated letters or end in a vowel? Or both? So we know that this cannot be the addition principle despite the word or, because this actually requires one or the other or both. So these actions can in fact be performed at the same time, and therefore we cannot apply addition principle. Something else has to be at work here. Let's see. We already know how many words there are with no repeated letters. We already know how many words there are that end in a vowel. We in fact even know how many words are with both of those properties. So this is beginning to look a lot like the union, the intersection, and the two separate sets together. Let's introduce a notation here so we can actually see the structure a little bit better. I have a set of words with no repeated letters, and I have a set of words that end in a vowel. So I'm going to give those things two different names for the sets. R will be a set of words with no repeats. V will be a set of words ending in a vowel. What this part of the question is asking is the number of words, so the actual number of elements in the set of repeated letters or, so the union, vowels. Remember that the principle of inclusion-exclusion tells us that this number will be number of elements in the first set plus the number of elements in the second set minus the number of elements in the intersection. Now, the good news for us is we already have all of those pieces we can feed into this formula. So the number of words with no repeated letters is 26 times 25 times 24. The number that end in a vowel is 26 squared times 5. And the number that have both of those properties is 25 times 24 times 5. You can plug this into the calculator and figure out the actual number. Counting is a really nice way to put together lots of principles that we've already considered. For example, sets, principle of inclusion-exclusion, and now the multiplication and the addition principle. It might seem overwhelming at first, but it gets better with practice. So let's practice with more examples. The deli has 5 different types of bread, 3 different protein options, 2 different types of cheese, and 10 different veggies. How many different sandwiches are possible if you select exactly one type of bread, protein, cheese, and a veggie? So exactly one type of each. So you're gonna have to pick a bread. So let's create a sandwich. I have to pick a bread, I have to pick a protein, I have to pick a cheese, and I have to pick veggie. And for each one, I have a certain number of options. For the type of bread, I have 5 different options. For the type of protein, I have 3 different options. I have 2 options for cheese, and finally 10 options for a veggie. I do have to perform these tasks all consecutively and all together, which means that I'm going to utilize the multiplication principle and multiply everything together. So in this case, if I multiply through, I should get 300. Next up, what do we have? How many different sandwiches are possible if you must select bread and protein, but you do not need to select cheese or veggie? So in this case, I had to select one of everything. In the second case, I can skip the choice for the cheese and the veggie. I could choose, but I don't necessarily have to choose. So I'm going to try to cheat a little, not efficiently here, but there we go. That is still my sandwich. Okay, excellent. The number of options for bread stays the same. I have 5 options for bread. I still have 3 options for the protein. But what happens with cheese now? I actually have 2 options for cheese, but I don't need to select it. So in fact, my options for cheese are 3. There are 2 options for the actual cheese and 1 option that does not involve cheese at all. So this one corresponds to none. No cheese is a cheese option. I also have a similar situation for the vegetables, right? There are 10 options for the veggie, but I don't need to select it. So I'm going to have 10 plus 1, where 1 represents none. So this is like a small example of the addition principle. I have 10 choices for the vegetable, or I have the 1 option for the non-vegetable, and these tasks cannot actually appear simultaneously. I either pick a vegetable or I do not. So now I do have to pick bread and a protein. I have to decide on cheese, no cheese, and I have to decide on what veggie or no veggie. So altogether, these are going to be connected by a multiplication. And I actually have the number here. It should be 495. Last part of this delicious question. How many different sandwiches are possible if you must select bread and cheese, but can only get one of protein or veggie options? So I can either get the protein or I can get the veggie option. So what do I have here? Well, I must select bread and cheese, and then I have an or. So it seems that my options are to select bread, to select cheese, and to select protein, or to select bread, cheese, and then a veggie. How many options do I have for each of these? Well, for bread I have 5, for cheese I have 2, for protein I have 3, and then bread, cheese, and a veggie. Within each of these, I will apply the multiplication principle because I have to choose bread, followed by choosing the cheese, followed by choosing the protein. And same in the second scenario where I have to pick bread and then cheese and then a veggie. So I can connect these all by multiplication. But these cannot occur simultaneously. I can only get one of these. They're connected by an or. So altogether, here, I'm going to have a plus. So my final answer will be 5 times 2 times 3 plus 5 times 2 times 10. Okay? Each part indicates what will happen if I go with either protein or veggie, and the overall answer represents of going with one or the other, but not both. Let's take a look at the next question. Canadian Cabinet, so the ministers, currently, as of I'm recording this in August, consists of 39 ministers, including the Prime Minister. 19 of them are female. We are wondering what we're going to do with all these ministers if we would like to arrange them in a row for a picture. Now they're going to be in a row, so my situation, if I want to represent it somewhat pictorially, is kind of similar to the situation with words from the previous page. I have a person here, followed by another person here, and so on, all the way down the road to the last person in the line. How many choices do I have to place the leftmost person? I have 39 ministers in total, so for the first position, I have 39 possible people options. What about the next position? Well, these are now humans, so they have to be distinct, so whoever I picked here is excluded from being in the next option, so that means that I only have 38 options for the person that will go into the second position. For the next one, I have 2 fewer options than from the beginning, and so on, all the way down to the very last position. And if I'm choosing people one at a time, there is going to be only one choice left for the very, very last position. So altogether, because I do have to pick all of them one at a time consecutively, my answer is going to be 39 times 38 times 37, all the way down to 1. Next up, how many arrangements like this in a row are there if the Prime Minister must be the first person from the left? So I still have 39 spots I have to fill, except for now, I am not given a choice of who to place here. I am told it must be the Prime Minister. So my options for the leftmost spot have been reduced to just being able to pick one person out of the 39 available. How many options do I have for the next one? Well, I have no restrictions who can go next to the Prime Minister, so all of the still available people are in fact available for the picking. There were 39 to begin with, 1 got placed here, so I have 38 options for the next spot. And continuing in a similar fashion, 37, 36, and so on, all the way down to the last spot, which will only have 1 option at the end as well. And again, multiplying all of them together, I'll have 38 times 37 all the way down to 1. If you compute these numbers, you will notice that this number is less than this one. There are fewer arrangements with more restrictions than there are total arrangements overall. How many arrangements are there if the Prime Minister must be the leftmost or rightmost in the picture? So this is only one of the options here, right? So I can actually take this, cheat a little bit, and copy it over. So I can have the prime minister being on the left, right? So this guy is my prime minister here. Or he could be the one person on the rightmost spot. So I can have an or, and then a sort of similar situation. So let's redraw it though from the beginning. So he will be the rightmost person. So the rightmost space doesn't have a choice. There's going to be exactly one choice for it here because it has to be the prime minister. Once we've placed him, we can start from left to right. So the number of people that can go into this spot is now 39 original ministers minus one that I've already placed, so 38. The next number will be 37, 36, and so on. Now, only one of these arrangements can happen. They cannot happen simultaneously. The prime minister cannot be at the same time the left and the rightmost person. So this is going to be connected by a addition principle. So I have 38 times 37 all the way down to 1 plus 38 times 37 all the way down to 1. So you will notice that these numbers are actually the same. The number of ways to place prime minister to the left is the exact same as the number of ways to place him all the way to the right, because the arrangement of the other people doesn't actually depend whether the prime minister goes leftmost or rightmost. Once the other 38 ministers arrange themselves, he can simply join to be leftmost or rightmost person. In how many ways can we arrange ministers in 2 rows so that all women are together and all men are together? So now we are working with 2 rows of ministers. Let's call them, for example, row 1 and row 2. They will stand one behind the other. All the women must be together. Let's arrange the women first. So there are 19 females. So for example, they can go into row 1. All the women go here. So let's say women, and then this one will be men. All the women will go into the first row, and so there are 19 of them. I will start off by picking the person who goes in the leftmost spot. I have 19 choices because all of them are still available for the choosing. So there's going to be 19, followed by 18, and so on, all the way down to 1. And then I can arrange men in a similar manner. I can pick the spots for them and then fill them in. Now, 19 of the ministers are female, so 20 of them are male. So the number of male choices will start with 20 and go all the way down to 1. Okay, so these are the 2 rows when they're filled in. And I actually have to connect all of them by a multiplication principle, because I will first place all the women and then consecutively I will place all the men. So I'm going to have 19 times 18 all the way down to 1, followed by times 20, 19 all the way down to 1. Now, the thing that I haven't addressed yet, though, is I simply decided to put women in row 1 and men in row 2. But the reverse situation is, of course, also possible. So I could have that men go in row 1 and women go in row 2. The number of arrangements for when men and women will not change, but this will give me yet another option. Now, of course, these are completely separate. You have to decide whether row 1 contains men or women, and they cannot happen both at the same time, which means that these 2 options will be connected with an addition principle. But because the numbers are going to be the same, it's simply going to be doing this exact same thing twice for the 2 different orders. Now, as I said before, I understand that this does seem a little intimidating at first. Counting is what requires a lot of practice, and you have to see a lot of different exercises before you get really comfortable with arrangement of different ways of constructing the designing and ordering of the different elements. The more examples we're going to do, the more comfortable it's going to become. Let's now take a look and think about what are the potential differences in different kinds of arrangements. So, part 1 here is asking how many different two-letter words can be made using letters A, B, C, D without repetition. So this we've in fact already kind of seen. If you were asking for four-letter words, I'd be able to write it out right away, but they're two-letter words. So maybe I can apply the same logic. I'm forming two-letter words. What are my choices for letter 1? Well, I have 4 available options. So for the first letter, I have 4 available choices. What are my options for the letter 2? I cannot repeat letters, so whatever letter I picked here cannot go here, which means that my options are reduced by 1. And because I have to pick first letter followed by the second letter, I'm going to multiply the 2 together and get the total as a 12. Now, great. One thing to observe here is when I am choosing, I actually have to do so in some kind of ordering. So for example, the two-letter word AB is not the same as two-letter word BA. And I will account for both of them using this type of counting. Let's take a look at part B here. How many different two-person teams can be made if only Alice, Bob, Chris, and Dora can play? Okay, so I have to think again in terms of arrangement, except for these are now people. So the team that contains Alice and Bob is exact same as the team that contains Bob and Alice. So I can't quite count the same because this will count this team twice. So because the numbers are fairly small, we can write out all the possibilities. So I have Alice and Bob on a team, which is the same as Bob and Alice. I can have Alice and Chris. I can have Alice and Dora. I can have Bob and Chris, Bob and Dora, and finally Chris and Dora. And this will cover everything. Every team here will not have the order imposed on it, as we've already noticed, right? So every team here will correspond to 2 different words if we were thinking of them in terms of words. This is why, while there are 12 options in the top, there will only be 6 options at the bottom. The major difference between the 2 examples is whether order matters or it does not. In the first example, the order matters. Words AB and BA are different. In the second question, the order doesn't matter because the teams are like sets. And so having the order does not make any difference at all. We're going to work with these 2 different things in 2 quite different ways going forward. So it's important to realize the distinction now. For our next 2 examples, we're going to look at something quite applicable. We're going to first talk about Internet Protocol and how it assigns addresses to each device. And we're going to count how many different devices we can actually have it use in any particular point in time. And then we're also going to talk about the defense mechanisms that are employed in the cybersecurity world, such as layered security controls and parallel approaches. Now, before we proceed, let's take a look at a video that explains how Internet Protocol or IP actually works on the internet. Pause this video here and first watch the video that is linked in the description. So just a recap, an Internet Protocol or IP assigns addresses to each connected device. So for example, me sitting at home right here recording this lecture, I have my computer, I have my iPad that I'm working on, and I also have my phone connected to the internet, which means that I myself am using 3 different IP addresses. There are 2 different versions of IP currently in use, IPv4 version 4 and IPv6 version 6 that everybody's trying to sort of move over to. We're going to go through each one, talk about the format, and discuss the number of possible addresses within each version. As mentioned in the video, IPv4 uses addresses in the form of 4 digits, each between 0 and 255. So I have 4 different, it shouldn't be digits, it should be numbers, and each is between 0 and 255. So if I'm going to count, what are the possible number of different IP addresses? I have to think of what are the possible options for each of the numbers. Each one of them is between 0 and 255. So there are 255 non-zero numbers, and together with a 0, the first number has 256 options. So does the second, because they don't have to be distinct. So does the third and the fourth. Now, because I do have to pick all of them in order, and generally they all have to be picked consecutively, I'm going to apply the multiplication principle here and multiply them all together. So 256 to power 4. Now, as the video also mentions, the computers don't actually work with numbers in decimal, they work with numbers in binary, which means that instead of recording a number such as 101, the computer will transform this into a binary and write it using zeros and ones only. My 101 choice wasn't a great decimal number to be illustrative, but for example, 255 has to be written with numbers that uses only zeros and ones. So instead of taking up one spot and maybe up to 3 digits in decimal, each one of these within the computer takes up 8 spots and uses an 8-bit binary representation of each of these numbers. So let's think about what that means in terms of how many different IP addresses if we think of them in binary. There are 8 spots here, and each one in binary has 2 possible options. This digit can be either 0 or 1. So I'm going to have 2 options for the first digit. 2 options for the second one, again, can be 0 or 1, all the way down to the last spot here. So again, I'm going to employ the multiplication principle and multiply them all together because I do actually have to pick all the possible digits. So this will give me 2 options for each of the 8 spots, or 2 to power 8. This is not terribly surprising because 256 is in fact 2 to power 8. Now this is just for the first number, and I have to repeat that for 3 of the others. So this will also correspond to 2 to power 8 options. The next one will correspond to its own 2 to power 8 options, and the last one will correspond to its own 2 to power 8 options. Again, multiplying all of these 2 to the 8s together, I have 2 to the 8 4 times over. If you remember your exponentiation rules, when you raise a power to a power, you multiply the 2 powers together. So I'm going to have 2 to power 32, which is exactly as claimed in the video. We notice that these 2 numbers, of course, are the same, and they both are about 4.3 billion. Now, as I am recording this video, there are about 7.7 billion of people on Earth, and most of us have more than one device. So this is most certainly not enough for our current needs, which is why the internet is moving to the IPv6 version. Let's count how many different addresses are available within that format. So the form is as following. I have 8 different spots, and each segment is a hexadecimal value between 0 and FFFF. Okay, so each of these spots is actually 4 spots in the middle where the numbers go from 0 to the largest hexadecimal number that can be written into 4 digits of information, which is FFFF. Okay, so each of these Y's is a 4-digit hexadecimal number. How many different options are there to pick one Y? Well, it's a hexadecimal number, which means I have 16 different options for the first digit, 16 for the second, 16 for third, and 16 for the fourth, which means that each Y altogether has 16 to the 4th options. Now, this is just each Y. Let's write that down. Each Y has 16 to the 4th possibilities or options. Now, this is just one of the 8 pieces, which means that altogether, if I pick, there are 16 to the 4th options here, 16 to the 4th options here, and so on and so forth, 8 times multiplied together, because I do have to choose all of them. So I'm going to have 16 to the 4th all to power 8, which is, again, raising power to a power means multiplying the 2 together, will give me 16 to power 32. Now, I would like to compare these numbers directly, which means that it would be better if I had the same base, because that would make the comparison easier. Now, luckily, 16 is also a power of 2. We've noted that in the section on binary and hexadecimal numbers. 16 is actually 2 to the 4th, which makes converting between hexadecimal and binary system a little bit easier. So 16 is 2 to the 4th, and that is raised to power 32. Again, power raised to a power will multiply each one. So it's 2 to the power 130 and 28. There are 2 to the power of 32 IPv4 addresses, and there are 2 to the power 128 IPv4 addresses. As the video points out, that is a huge number. It's 340 trillion. So it is most certainly enough to sustain humanity for basically as long as the Earth can sustain us, and a lot longer than that. This is the protocol that the current systems are moving forward, because IPv4 is not enough for our current usage of the internet. The next example here is going to talk about network security approach. So not just distributing addresses, but protecting the actual information. There are two different types of defenses. There is a layered defense, also known as the castle approach, and then there's parallel defense. The castle defense is usually pointed out as being more secure, and we would like to find out why that is the case. The reason it's called the castle approach is if you picture yourself a castle, a castle, maybe I'll find a better picture. The castle walls protect the castle, but the other infrastructure around the castle also protects it. For example, there might be a moat, there might be another gate, there might be something else. So there's a whole layer of defenses that an attacker has to go through one at a time before they get to the actual inside of the castle. Similarly here, we're going to think of having an attacker. He looks pretty innocent. That's the best I can draw. We're going to have to think about different controls we're going to put in place on the path between the attacker and a server that he's trying to hack. So here, we're going to think of the layered approach. So I'm going to have two different defenses. Let's say I have control A, which is going to be 70% effective at stopping the attacker. And then I'm going to follow it with placing a control B, which will be, for example, 80% effective at stopping the attacker. What I would like to do is figure out, with these defenses in place, what is the probability of attacker breaking both and actually hacking my server? So what are the different options? I have two different controls here. So my attacker can do what? Well, the attacker can defeat A and then carry on defeating B. And I'm going to calculate this in a second. I just want to write out all of my possibilities first. The attacker can defeat A, but not B. That will get him here, but not over here, which means that he's not actually going to succeed in getting to the server. The attacker can defeat B, but not A. Well, that is essentially useless, because if he can defeat this layer, but not this layer, he's never going to actually get to B in order to defeat it. Okay, so this right away is going to be 0% possibility. And the final option is he's not going to be able to defeat A, and he's not going to be able to defeat B. I'm going to at least figure out what the actual percentages that correspond to these situations are. Now, let's think about which scenario is actually dangerous. So which one of these scenarios will get attacker successful in hacking our server? If he defeats both A and B, he will end up being at the server. So this case is a red flag. This is not a good scenario for us. What about the next one? He defeats A but not B. That means that the B prevents him from from carrying on. It actually succeeds in stopping him. So this will prevent the server from being hacked. B not A is completely useless. Neither of them means that our defenses worked at the first step. So out of all of these, in only the first case is the attacker actually going to be successful in hacking our system. So let's figure out how often does that actually happen? What percentage of the time does that occur? So what are we going to have here? The attacker must defeat A, and he then must carry on forward and defeat B. The control A is 70% effective in preventing an attack, which means that the attacker is going to be able to hack it in 30% of the time. So 0.3. Once the attacker defeats A, they must carry on to control B. Control B is effective 80% of the time, which means that 20% of the time it will be hackable. Now, the attacker must defeat them one after another. So my multiplication principle is at work here, and I'm going to multiply my two probabilities together here, which will result in 0.06, which corresponds to 6%. So 6% of the time, this layered approach will be broken and the server will in fact be attacked. Now I'm gonna actually find the percentages for the rest of the cases just so I can double check myself, because these are all of the possibilities. All of the percentages actually have to add up to 100, and this is going to be another way of me making sure that all of my arithmetic is correct. So if the attacker is going to be able to attack A and not B, what is that represent in terms of probabilities? They're able to hack A, which is secure 70% of the time, which means that they're able to hack it 30% of the time, but they will not be able to hack B. The control B is effective 80% of the time, which means that it will stand strong. And so one after another, control A being hacked, control B being not hacked, will give us altogether 0.24 or 24% chance of success. And then finally, we already decided that this is going to represent 0, but the last case here, we will not defeat A and we will not defeat B. Now, that means that the attacker didn't even get past the control A. So control A actually stood strong at 70%. The attacker did not manage to, in fact, attack it, and so they would not be able to carry on through, which means that in this particular case, we won't even be able to get to B to calculate the percentage of attack there. So this is secure 70% of the time. Now, adding up all of our numbers together, we see that we end up with the total of 100, which is reassuring that we've done our math correctly. So once again, with this layered approach, the attacker succeeds in hacking the server 6% of the time, because this is the only case when that can actually happen. Parallel defenses, much like parallel digital circuits, don't work in series, but rather work in parallel. So let me copy over this picture, but in fact, move it around so I have a parallel approach. That means that the attacker can either choose to attack control A or control B, and either of those approaches will lead the attacker to the server. So they can decide A or B, and if they break one, they will be successful in getting to the server. Okay, let's move this picture over to the side, and I'm going to repeat reproducing my table here. So what do we have? We can defeat A and B, in which case we are, of course, going to get hacked, right? If the attacker defeats both, well, just one path is enough. So if they defeat both, then this is certainly not good for us, because then we can't even close one gate and hope that the second one keeps us secure. Attacking A but not B, well, if they are able to get through A, they will still be able to get through to the server, which means that the second scenario is also corresponding to being hacked. Next, they're able to attack B but not A. Well, same issue. If they're able to attack B, they will still be able to get through to the server. So this will also represent the case of being hacked. And finally, not A and not B. So they got stopped by A and they got stopped by B, which means that this is the only case when the server does not get hacked. This is already troublesome because we can see that there's only one case in the layered defenses approach that attacker succeeded through, whereas there are 3 cases in the parallel defenses approach where attacker was successful to get into server. But maybe the percentages of success here are lower. So we're going to have to calculate it to figure it out. Defeating A and B. So this is actually going to be very similar. I'm going to be able to get through both of the scenarios, means the attacker broke defense A and they broke defense B, and that will be successful 6% of the time. The next up is they were able to break A but not B is again going to be the exact same calculation because this doesn't actually really depend on the architecture. So this will be successful 24% of the time. But in the other 2 cases where we were able to reason out what happens here, the analysis, the attack path analysis here is going to be different. They're able to defeat B but not A. So they were able to get through B, but they were stopped by A. The probability of defeating B is 20%, so that's what I have here, but probability of not being able to get through A, that A stands strong, is 0.7, which overall results in 14% chance of getting through this way. And finally, the only time that the attacker is not going to be able to get through this to the server is being able to neither defeat A nor B, which will happen 70% of the time with A, they're not going to be able to get successful, and 80% of the time with B, they're not going to be able to get successful, which will happen 56% of the time. Okay, so comparing overall, hacking in the layered defenses approach happens 6% of the time. Hacking in the parallel defenses approach happens 6 plus 24 plus 14% of the time. Or you can actually think about the complement. 100 minus 56%. This, you're secure 94% of the time. This, you're secure 56% of the time. So if you're going to structure your defenses and you're going to pick only one of the architectures for your controls to use, make it a layered defenses approach. Castles are built that way for a reason, and maybe this is a good lesson to take into the network security as well as the medieval castle security.